frictionless as much as we can imagine. I mean, it's not gonna be totally frictionless, but that's the whole point of it being on the snow, that it's, you don't have to, we've simplified the problem so that we're not working against a friction force.
Yeah.
And he's pulling with a force of 50 newtons, exerted at an angle of 38 degrees above the horizontal. Find the horizontal and vertical components of the force and find the work done. So let's do the first part first, okay? So here's the snow and here's the string, and we're pulling with 50 newtons. Again, the units of newtons are a unit of force. It is kilograms times meters per second squared are the, like if you break the units of Newton down, it's mass times acceleration due to gravity is kind of really where that's coming from. So it's kilograms times meters per second squared. All right, so we are being asked to find the components. So if you're not told otherwise by having some picture drawn, you're going to assume that this is the origin. Okay, and the way they've written this problem, it's really a two-dimensional problem. The sled is going this direction, we're pulling kind of straight up in the same plane. So we can interpret it as a two-dimensional problem. So one of the things we did at the end of class on Tuesday was talk about how you can find the horizontal and vertical components by recognizing that you have a right triangle situation and cosine of this angle is equal to adjacent over hypotenuse, and my hypotenuse is my force. And so 50 times cosine of 38 degrees will be the force in the horizontal direction. Okay, so the horizontal direction is adjacent to the 38-degree angle, so 50 newtons times cosine of 38 will give me, what is it again, we're on 59 point what?
No, 39.4.
30.
39.4 newtons.
40, thank you. Okay, and then sine of 38 is opposite over hypotenuse. And so 50 times sine of 38.
30.78.
30.78, right? I guess I'll just put 8 since we rounded down to the tens.
Well, actually, that one, the other one is rounded to the hundreds. It's just
Oh, it's 40,
zero.
okay,
Yeah,
okay.
it's 400.
Okay, okay, so this one should be 70, sorry. Thank you. All right, so that's, again, just reviewing horizontal and vertical components. So basically, 39.4 newtons are actually moving the sled horizontally. The other 30.78 newtons are just going, they're going in the vertical direction, so they're affecting something else and not the sled moving in the horizontal direction. The definition of work, again, should have been introduced in Calc 1, but that could have been a while, or you might not have gotten into it. So work is, in terms of physics, is defined to be force times distance. And the force you're going to focus on is the force that is directly related to moving something a certain distance. So the 39.4 is the force that's moving the sled horizontally. So it says we move the sled 15 meters. So we multiply by 15 meters, and 39.4 times 15 is it's a Newton meter. A Newton meter is also called a joule, named after a physicist who worked in this. Now, I approach this somewhat from the trigonometry approach, like this topic's also slid into trigonometry in the right triangle sections of, and vector sections of trigonometry. If you answer the question from a physics point of view, then force is a vector, the distance is a vector. In this case, the vector that's affecting the direction that the sled's moving is just x 39.4, y 0. Okay, because I'm just moving the vector, I'm moving this direction. And the distance I move is 15, I move vertical 0. So if I found that dot product, okay, so this is the dot product between this vector and this vector, so we're treating these as vectors now. You multiply the like components, so I would multiply these two together, and it would give me the same answer we just had, okay? So I'm just trying to point out that sometimes your vectors are simple enough that you could actually kind of ignore them as vectors and get an appropriate answer. But technically the physics definition is treating force as a vector, treating distance as a vector, because sometimes the situation's more complicated than the one we have here. But if I do treat those as vectors, I still get the same answer. Okay?
Isn't the general formula for work is force times distance times cosine theta, right?